Since we have a multivariate problem, I'm going to begin by drawing a picture. I think it's particularly important to draw a picture for a problem like this, where I want to find the maximum of two random variables. We are told that x and y both range from 0 to 2, so my domain here is a square domain, which gives me at least the possibility that x and y are independent, although actually it turns out in this case that x and y are not independent, because our joint density f of xy does not factor into a function of x times a function of y. Rather, it's a function of x plus a function of y. So we're going to have to do this problem sort of one of the other ways we can deal with maximum problems, and that is to break the problem down into cases. If I draw the line y is equal to x, then if we're below that line, here we have y is less than x, so therefore the maximum x and y is going to be equal to x. Above the line, y is greater than x, so that means that the maximum of x and y is going to be equal to y. So essentially, therefore, I have two cases. I can say that the expected value of the maximum of x and y is going to be equal to the sum of the integrals, each one corresponding to each case. One case is going to be the x less than y case, and the other case, or let's actually do y less than x, sorry. And the other case I'm going to have is when y is greater than x. When y is less than x, that's my bottom triangle. So x ranges from 0 to 2, y ranges from 0 up to x, and my maximum in that situation is x. So I'm going to do x times the joint density f of xy, integrating this dy dx. What is my other case where y is bigger than x? That's my upper triangle. So here, I would prefer, if possible, because it's going to make my integral a little bit easier, to use 0 as my lower limit as much as possible. So here I'm going to let y be on the outside, have y go from 0 to 2, and have x go from 0 to y. So here I'm doing my integral dx dy instead of dy dx. And now in this second integral, what am I integrating? Here y is greater than x, so I'm going to integrate y times my joint density. Now, one thing you might notice about our joint density, f of xy, this is something that actually is symmetric in x and y. In other words, if I were to replace all my x's by y's and all my y by x's, my x squared would become y squared, my y squared becomes x squared. That doesn't change my joint density. My domain is a square that's symmetric in x and y. That would not change. The two cases I'm dealing with my integrals, those are also both symmetric in x and y. So by symmetry, what do I get? By symmetry, I can just combine these as just saying it's 2 times one of the integrals. Let's just do the first integral just to pick one arbitrarily. So x goes from 0 to 2, y goes from 0 to x, and I'm integrating 3 over 32 times x cubed plus xy squared integrated dy dx. What are those integrals going to be? Well, the integral of 3 over 32 times x cubed integrated with respect to y, that's a constant as far as y is concerned. So it's just going to be the length of the interval x times that constant I have. So that's going to give me 3 over 32 times x to the fourth. The integral of xy squared, that's going to give me 1/3 xy cubed. Evaluated from 0 up to x is going to give me 1/3 x to the fourth. So I'm going to have 3 over 32 times 1/3 x to the fourth. And now all that needs to be integrated dx. So what's the integral of that with respect to x? Well, I have a bunch of x to the fourth. So let's actually factor out all of my constants. 3 over 32 plus a third of 3 over 32. 1/3 times 3 over 32 is 4 over 32. Sorry, is 1 over 32. The 3's cancel out. My sum ends up being 4 over 32, which is 1/8. Multiplied by 2 becomes 1/4. So I have 1/4 integral 0 to 2 of x to the fourth value integrated with respect to x. That's going to be 1 over 4 times 1 over 5 times 2 to the fifth. In other words, I get 32 over 20, which evaluates to 1.6, and I have answer choice E.